Now it's time to assign some numbers to the manufacturing of aluminum cans. This will allow us to calculate the CO2 emissions per can. In the first row of this data table, we can see that one aluminum can has a mass of 16.8 grams. The electrical energy required for can manufacturing for only the shell and the lid is measured in megajoules per kilogram of cans, and it has a value of 4.6. The electrical energy required for rolling to transfer a big block of aluminum into a nice thin sheet is measured in the same units but has a value of 2.0. The amount of primary Al or aluminum required per can is 1.07 kilograms. Raw bauxite ore to primary aluminum is measured in kilograms of bauxite per kilogram of primary aluminum and has a value of 5.3. The amount of diesel fuel required for bauxite mining and to refine it into primary aluminum is 0.0011 kilograms of diesel per kilogram of bauxite. And the electrical energy for transferring bauxite ore to primary aluminum ready for manufacturing is measured in megajoules of energy per kilogram of bauxite and has a value of 0.17. The diesel carbon required for this process is measured in kilograms of carbon per kilogram of diesel and has a value of 0.85. The electricity is measured in kilograms of CO2 per megajoule and has a value of 0.28. This is all perhaps easier to visualize as an equation. Emissions per can using the following equations. First, we have the amount of CO2 per megajoule of electricity, which is 0.28. Next, we multiply this by the megajoules of energy required per kilogram of bauxite, which is 0.17. Multiply again by 5.3 kilograms of bauxite ore per kilogram of refined aluminum. Multiply this by 1.07 kilograms of aluminum per kilogram of can, and then convert the units by multiplying by 1 kilogram per 1,000 grams. And then multiply this by 16.8 grams per can. This results in a value of 0.0045 kilograms of CO2, which in more practical units is 0.45 grams of CO2. Next, calculate the CO2 emissions associated with the electricity needed for rolling the big block of aluminum into a thin sheet. The numbers here are 0.28 kilograms of carbon dioxide per megajoule of energy multiplied by 2 megajoules of energy per kilogram of can multiplied by 1 kilogram per 1,000 grams to convert the units multiplied by 16.8 grams per can results in 0.94 grams of CO2. Next, calculate the CO2 emissions associated with the electricity needed for can manufacturing. The result is 2.16 grams of CO2. We'll now see how this translates into the CO2 emissions per can as an equation. First, we have the kilograms of CO2 per megajoule of energy multiplied by 0.17 megajoules of energy per kilogram of bauxite ore multiplied by 5.3 kilograms of bauxite per kilogram of primary aluminum multiplied by 1.07 kilograms of aluminum per kilogram of can multiplied by 1.1 kilogram per 1,000 grams to convert the units multiplied by 16.8 grams of can. This results in 0.45 grams of CO2. Next, we need to calculate the CO2 emissions associated with the electricity needed for rolling the aluminum into the can form. The following equation shows that 0.94 grams of CO2 are required for the rolling process. Next, we need to calculate the CO2 emissions associated with the electricity needed for can manufacturing. This results in 2.16 grams of CO2. Finally, we see the total CO2 emissions for raw materials and the processing is 3.55 grams of CO2 per can. The units cancel as follows. The following data will be required for your LCA. First, you'll need to know all the materials that are within your product. Knowing the specific details in the material will be necessary in order to complete an accurate LCA. Knowing the difference between specific materials, such as metals and plastics, is quite apparent. However, the finer details of differentiating between low-density polyethylene and, for example, polyvinyl chloride are somewhat more difficult. They're both a plastic, but depending on which one you think it is, it'll have a different CO2 per kilogram value. You'll also need to know the mass of each material for your project. One way to do this is to weigh each part using a mass balance. However, since you've probably already assembled much of your project, it would be a hassle to disassemble it only to weigh it, and then having to reassemble it. So another way of doing this is to find the volume of each part using SolidWorks, and then using the density, calculate the mass. Because you need to create every part in SolidWorks for your final submission anyway, this is likely the more time efficient method of calculating the mass. In the SolidWorks software, you're able to change the material from the default to any one of a large number of materials. If you select the material that your part is made of, it will then tell you the mass without having to do a separate calculation using the density. You'll also need to know the CO2 per unit mass of material. This is what we've done for the previous steps in this presentation. However, there are many sources of values for a wide range of materials published digitally, and this is what we'll use for the teddy bear wheelchair project and your submission for this lab. This simplifies things because we are not expecting everyone to be an expert in the manufacturing process of many different materials. There's an Excel spreadsheet on CourseLink called LC Data for TBWC, and it's what you'll use